everybody. So now we're going to start talking about a new type of classification algorithm, which goes by the name support vector machines. And this is a technique which is really based on geometry, and it'll involve some new ideas that we haven't talked about yet. Like all classification algorithms, there's an optimization step involved. You want to find the best something. But here, the best something that you want to find isn't really a calculus problem. It's a different kind of optimization problem, and so we'll get a chance to look at some convex geometry. But let's start at the beginning. So as I mentioned, a support vector machine is an algorithm for classification of data, which is based on geometry. Just at the beginning, let's be clear, I have no idea why they're called machines. It's just an algorithm. There's no machine. And unless you like to think of an algorithm as some kind of a machine. But anyway, a better name for them would be something like optimal margin classifiers. And you do sometimes see that used in the literature. One of the advantages that these types of algorithms have is that once you fit them to the data, they're very quick to evaluate. So if you're trying to distinguish between dogs and cats, and you've run this algorithm to construct an optimal margin classifier or a support vector machine, which can distinguish between dogs and cats, and then you give it some new data and you ask, is this a dog or a cat? It's very quick to do that calculation. And that's an advantage if you're doing a lot of such classification in production. And that's one of the reasons why people find these methods attractive. So how do they work? What's the idea? Well, let's start by looking at some of the penguin data. So this is a little excerpt from the Palmer Penguins data set that we looked at briefly during the PCA lab. And what I've done is I've plotted the culmen depth versus the body mass for two different species of penguins, the Adelie penguins and the Gentoo penguins. And you'll notice that the Adelie penguins, the blue ones, are all down here, and the Gentoo penguins are all up here. So they fall into two clusters based on these two features. And in case you're interested, the culmen depth, if you look in the penguins' GitHub site, you'll see that they have this nice picture, and they show you that the culmen depth is really the depth of the penguin's bill. So that seems to be an important feature for distinguishing between penguins. So we want to find a classification algorithm that will allow us to distinguish between Gentoo and Adelie penguins based on this phenomenon that they fall into different clusters on these two features. And here's a very simple way to do that. Let's just draw a line between the two sets and use that to distinguish between the two classes. So I did this by eye. This is the line in these coordinates, y equals 1.25x plus 2. But because of the way the coordinates are, the y coordinate, you have to multiply it by 200 to convert it to grams. In the original coordinates, this is y is equal to 250x plus 400. In other words, if you look at this picture and you're above the line, so if you're up here, you are a Gentoo penguin, and that means that your mass is bigger than 250 times your bill depth plus 400. So this is the region where y is bigger than 1.25x plus 2, and this is the region where y is less than 1.25x plus 2, given that x is your mass divided by 200. And so here's our very simple classification algorithm. You catch your penguin, you measure it, I compute this value, 1.25 times its bill depth plus 400. If its mass is bigger than that, it's a Gentoo penguin. If its mass is less than that, it's an Adelie penguin. Now, of course, it's not going to be perfect because there might be some penguins that are outliers, but we didn't happen to catch any in this particular set of training data. So there's actually a separation between the blue and the green dots. Now, if we were going to try to evaluate the line that I picked, there's lots of lines that I could have drawn. For instance, I could have drawn instead, let's use a different color. How about green? How about black? I could have drawn this line. And that would have also separated the two sets. And it would give me a different criterion for distinguishing between the Adelie and the Gentoo penguins. So what kind of criterion could we use to say that a line is the best separating line? And that's where this term optimal margin comes from. So the margin, if you have a line like this and two sets of points, the margin is the gap between the closest points on each side of the line. So, but measured perpendicular to the line. So I'm going to blow this up a bit here. If you look at this, my original red line, this, if I measure from this closest blue dot to the dotted line, and I mean, I'm eyeballing this, but maybe from this closest green dot to the line, that gap, which I get by taking a parallel line on either side through the margin, through the closest points. This gap here is called the margin. It's the perpendicular, and its width is the perpendicular distance measured relative to the separating line between the closest point on one side and the closest point on the other. And one thing you could use as a criterion for the best separating line is it's the line which has the biggest possible margin. In other words, you want to draw the line so that if you were to move the line a little bit in either direction, you have as much space as possible, but before you hit a green point moving in one direction or a blue point moving in the other direction. And if you do that, if you've made the margin as big as possible, then that's called an optimal margin classifier or a support vector machine. So the problem that we are going to give ourselves is we're going to have two sets of points. Now they're going to be in a high dimensional space. And we're going to try to find not a line, but a hyperplane that passes between those two sets of points. And we're going to choose that hyperplane so that if we look at the closest green point on one side of the hyperplane and the closest blue point on the other, and we look at the perpendicular distance measured across the line or the hyperplane, that's as big as possible. And if we can solve that problem, then we will use that hyperplane as our classifier. If you're above the hyperplane, you're in one class. If you're below the hyperplane, you're in the other class. So that's the strategy that we will take up in the lectures to come.